All right, now it's time for our final panel.
I'm a senior RSE at the Institute for Computing for Climate Science at the University of Cambridge. And I do not know a lot about health and data science in action, so I've got a couple of questions. To start with, so we had a really nice talk yesterday from Raphael about energy-aware scheduling and energy-aware computing, and in the data science applications, especially neural networks, we know that it's always very expensive to train the networks, but it's quite cheap then to actually do the predictions. And if you're talking, so I think both Peter and Bartosz were talking about basically individual per person models. So where do you think we would be there in terms of need for resources, and then also to talk to the other two of you, so where do you think are your resource needs, and how energy aware is your computing, and do we basically burn our planet while trying to do our research? So I don't know who wants to start first.
Well, in terms of the work that I did in the ICU, the two models that we used they're very shallow in terms of the layers. So the actual computational power that they needed, there's not a lot of computational power needed. The utilization that we saw on the GPUs, for example, was only about 20 to 25% of the GPUs being utilized for the grid searching, for example. So we weren't seeing very heavy workloads for that. In terms of future work, obviously it's hard to say if that would be memory dependent, because we'd be looking at up to 32 patients, and in my work we only looked at one. So for me it'd be quite hard to say, unfortunately. Okay,
Peter, can you say more?
I mean, I mentioned it as well. I think everyone realizes that. I asked the person who was giving that talk, who was only talking about HPC, or let's say I reminded him that people are expecting to are placing orders for data centers now to deal with large language models that are going to be requiring 3 orders of magnitude more than Frontier, which is the largest supercomputer, right? We're at 20 megawatts at this moment in time, right? They're planning for those. And the question is, how do we resource that? And we're hearing of nuclear reactors being developed, and the hope that fusion might come to the rescue. But this is very serious. I mean, it is making this business the most expensive in energy of any sector. And a lot of it is hidden, but the tech companies are driving it forward. So I don't think there's an immediate answer to this problem. It raises questions as to whether it's worth it as far as the planet is concerned. What are these models actually giving us that's useful? And that's a debatable topic, right? So there's moral and ethical, there's the legal issue. Do you remember? Should these large language models have a legal duty to tell the truth? Because people are basing a lot of things on them, and at the moment they're not very good at being accurate, despite all the hype. But the hype is telling us that in the next 3 or 4 years we will have something much better than what we're seeing today, but it'll be more energy consumptive. So I think there's a serious problem there that's not being properly addressed. It's bigger than we can talk about in this meeting. It's a political issue, and it has to be raised. But I would just say one thing, that my brain, at least as far as I'm aware, operates at 20 watts, whereas Frontier is 6 orders of magnitude more, and we're talking about it being artificial intelligence. We don't actually understand the meaning of the term intelligence, so it's hard to know what artificial means, but nonetheless, artificial intelligence at that cost isn't really matching the human brain. But there's an issue there that I believe we should be paying much more attention to. Our brains are analog devices, and analog computing, although it's disappeared and gone out of fashion since the Second World War and the development of the digital computer, should be remembered because it's so much cheaper to address problems that way. They're tougher, but people haven't invested much effort in them. But I can give you many examples of mathematical, modelling problems where we don't necessarily believe that the digital solution is correct. But no one tends to think about it because they say, put the calculation on the computer and whatever comes out of it must be correct. This is ludicrous. Okay? But,
should we ask Peter to give a talk about that next year?
With a continuum, we know there are examples in dynamical chaos. Chaos is all about extreme sensitivity to initial conditions. Well, if you follow a machine learner and we don't want more than single point or half precision floating point numbers, but single precision, I know there are 4 billion floating point numbers between minus infinity and plus infinity. In a large language model, we agreed there are trillions of parameters, so the number of parameters exceeds the number of floating point numbers, never mind the actual numbers. But that, 1 million of those 4 million is between 0 and 1, and another million is between 0 and minus 1. There's a really large number there. The rest of them up to infinity, there's a billion. So that's not a very good map. There's huge gaps. And if you have a chaotic system, what the hell are you doing with the ones that aren't on the map? So we know for simple systems, they don't capture it correctly, but an analog system would, and it's much cheaper. We should be thinking about it.
Thank you.
I think that's one of the exciting things about quantum computing. If we ever get to a large-scale quantum system on a realistic timescale, i.e. less than fusion or something like that, it is that, one of the problems we've been looking at recently is modelling, particle modelling, very grid-based particle models. And for every grid point, you've got the velocities and the positions of the particles at that grid point. Each represented by a floating point number, and for some reason we've been using 7-bit floating point numbers within this quantum computer. But then once you've got that specified, if you want to add more grid points, every logical qubit that you add doubles the number of grid points that you've got. So you very rapidly increase the scale, and this is where quantum computing, when it becomes large scale, really starts to win, because you add one more qubit and you double the size of your problem. So that can really help on your data. Now, you do have lots of problems to do with reading the data out and that sort of thing, but that's potentially, there is something there that will help with energy usage in the future, but we're not there yet.
Yeah, how hungry is energy hungry is quantum computing? I've got no idea whatsoever.
It's difficult to give a proper answer to that, because partly it depends on the technology. At the moment, they're not miniaturized or anything like that, but you've got all sorts of different ones, light-based or neutral atom-based and all sorts of other ones, and they've all got different. So it's hard to say what will win out in, say, 10 years' time or whatever, but yeah. I imagine at some point you'll be able to buy a CXL card that will fit in your computer, will have a quantum computer in it, and do some stuff, accelerated stuff for you.
Yeah, Peter, did you want to add?
You may not realise, but in fact 2 of my PhD students won the IBM Quantum Computing Prize last year, so it may be news to you, but we do quantum computing as well, and we've been using IBM's devices. The problem with them is that, as we know, they're far too noisy and prone to error generation. So every time you do a calculation, to get anything like the signal from the noise, you have to do huge numbers of these things to get like an ensemble average that gives you anything at all. So it's embarrassing, as well as the coherence time for the calculations, which is in the microsecond domain. That's the time when you can actually have the computer doing a quantum calculation is so small. You end up having to perform huge numbers of these things repetitiously. So they are pretty expensive. You're keeping them at close to 0 Kelvin. It's not a realistic proposition at this point in time to claim that that's going to compete with even these conventional computers. Of course, we all hope that in the future sometime it will look better, but we have to be able to do more serious things than we are currently able to do with the devices to talk about them seriously at this point in time.
Okay, thank you. Weiguang, do you have something to add to that discussion?
I can, first, to that question, I can add from my experience that from the astronomy simulation group that we are mostly heavily still relying on the CPU calculation, and generally that is very costly, I would say. And I don't know how the future will look like if you switch to GPU or some other kind of technology. But right now, I think we are still burning a lot of CPU hours, and that is not, say, very efficiently, maybe. But from the work I present, to use the GPU on the, of course, first is a very small sample, and we are relying on very small statics and to do work, and that is basically cost nothing. But the simulation itself is the most important part right now. And regarding to the, do you mind if I divide it a little bit to other things?
Depends on what it will be about.
Because several things come to my mind.
If it's relevant.
You have to decide.
Yes, okay. Okay, just a very small issue that I mentioned that machine learning can be used as a tool, and it doesn't matter whether you calculate with counting your figures to do things. But recently I read the news and I verified myself that you put two large numbers to ChatGPT, it won't give you the correct answer. Pay attention to that.
Yeah. We've got, do we have a microphone? We've got actually questions in the room.
Thank you. Yeah, on that point, on the two large numbers thing, I mean, the transformer architecture was invented to better translation, you know, so it wasn't necessarily to do with numbers or adding numbers together. But I do have a question about, so you talk about whether it's worth it to, you know, whether these large language models are worth it, especially with how much energy they do consume. Is your point of view that we should genuinely review as to whether we continue training these at all, or whether we should plow lots of money into making it more energy efficient and fixing the problems that are currently available? Currently there. Sorry.
I mean, it's my personal opinion that they're not worth all this effort.
So you
I'm not
call
that
to
keen
stop
on
training them?
Yeah, I mean, I believe many people think, but it's my personal opinion that hype has taken control of the agenda here, and these things are supposed to be sensationally good. We're meant to believe, you know, AI is transforming everything. It's not capable of doing that at the moment. And the price of trying to drive it further is just bigger models with more parameters. And the parameter part of this point I made in my talk, and I want to remind you, to be sure that these models make sensible predictions, which isn't on the trained stuff they learned. And with all these parameters, wouldn't you expect them to do some good predictions? They're just fitting data with a huge number of parameters. The issue is, how reliable are they on new stuff? And we have no quantitative measure of that. And those kind of questions need to be nailed down before we just produce even bigger models that look fantastic but are still unreliable. These are the big questions before going further with this technology, in my opinion.
That is a very interesting view. I would say the fact that OpenAI and other companies has access to the compute and academic institutions don't necessarily does make that very difficult to study.
It does. That's also an obvious drawback, that the agenda is being set by a small number of American tech companies. We have astronomical wealth and influence, some of it completely unaccountable, and the technology is moving so fast that the legal processes can't keep up with them, so they'll go on scraping the internet before anyone realizes that's not a good idea. But beyond that, you know, the next phase of this, which people are talking about, is to overcome the problem of polluting the internet with crap. But beyond it being so smart that they will come up with the scientific theories, because this is where it's going, that they can do science better than we do normally, we will be able to not just build foundational models in the technology sense, right? It's different sectors. You go to the Oracle, speak conversationally, and it generates all the science you ever need to know. So you don't really need to study science anymore, but that they will actually be able to create theories, even equations. And then in order to do the large language model, they will then do all the training on some forms of powerful computers that produce this wonderful self-contained area of new knowledge. And that'll just further suppress the need for other forms of science. This is seriously being promoted.
Do any of the other panel members have an opinion on that? Yeah, Alastair.
So one comment I can make, actually, you probably noticed recently if you use Google that it started adding at the top of the search results some AI search. Now that's obviously probably not something that, I don't know, sometimes might be useful, but most of the time it's probably not. Most of the time you probably want to ignore it. And there's with most web browsers a very simple thing you can do that just adds a little string to the end of your Google search automatically that will turn off that AI, and so that extra energy that's being used is no longer being used. And I think it's as AI becomes more and more prevalent, we have to think about what the energy usage of it is, and it's probably morally right for us to try and avoid using it if that's possible. So, and use it, of course, by all means when we actually want it. But if it's being there forced upon us and we don't want it, then we can take that little bit of an action to switch that off. It'd be worth doing.
Can I just give one example where it has been incredibly useful for me? So I've been a Python coder for 15 years. I've studied it for a long time, and it recently came up with a solution for PyTorch, for PyTorch's own source code, which sped up some of the training. And I tried to come up with that solution myself 6 months ago. It was really difficult, and it pointed me to a completely new path to look down, and that I did not find when Googling, myself. So it's quite interesting that it's able to, if people can use it well, able to point people down paths that they wouldn't have thought of.
No, it's definitely, I'm not trying to say this isn't a good technology, but it's got limits to it which we don't properly understand, and we need to. And it can do things like that, but it also does things that are hyped to claim their discoveries. And nature is partly to blame for the hype, because it publishes papers by these companies that claim things in both quantum computing and machine learning, which other smart people suddenly, when they see the paper, point out can be done by classical means. And this kind of thing keeps happening. It's part of something that isn't a good situation to be in, and the latest example of that was the AlphaFold 3 release. AlphaFold got a Nobel Prize, but the third release in May this year, Nature, having talked up the importance of reproducibility and the availability of the source code, pointedly cooperated with Google not to release that code. Why?
And we have one question over there and then one here.
Yeah, I just wanted to add to the conversation, when we're looking at trustworthy AI and the OECD guidelines for trustworthy AI, and, the big part of that is assessing environmental harms of your AI systems, and that should be a key part of any organisation's AI governance, is effectively, and what I advocate my customers is doing an environmental ROI on their AI projects. So is it worth the fuel burn that you're doing?
And that's probably a good question to ask ChatGPT, isn't it? It also happens to be very good for doing risk assessments. So if you're not keen on doing risk assessments, just do it that way. You don't have to read them anymore. You just generate them, copy and paste, and send them off. Genius.
Yeah, I was going to ask a question around the limits of AI, and I think one of the big differences is modalities, because humans are able to understand multiple different concepts. They can understand the mathematics, they can understand the language, they can understand the physics. Actually, that sort of stuff doesn't really inherently exist within an AI model in terms of multiple modalities. I think we've got language models and they do language. We might have other models that do other things, but they're all a little bit focused on one area. So the question really is, That's probably where the limit of AI is. But is there anything that could be done with, I don't know, HPC? Because HPC seems to understand modalities quite well. Simulations have lots of different parameters in them. To maybe make a more sort of, I suppose, curated set of capabilities rather than having all these kind of language models that go off and do their own thing. Does that make sense as a question? I'm not sure it's a good question.
Bartosz, you're very quiet. Do you feel you want to say something?
Well, I think in terms of HPC, as you say, it could play a very important part in this. I wanted to sort of comment on the last little bit, but I feel like there's been quite a big hype in AI. I mean, I know, and I was recently just a student. I'm sorry to divert slightly, but I was just a student just last year, and it feels like AI has just sort of came out of nowhere in Queen's University for me. So whenever I was doing my undergraduate studies, they had AI wasn't even really mentioned up until I'd done my master's, which was 5 years in. And I feel like lots of people are now looking at AI just because, it's the cool thing, it's everyone's doing it, and as you mentioned with the Google searching, now you get that whenever you do a Google search. So it's really important to look at AI in a responsible manner, as been mentioned by everyone.
Okay, thank you. Maybe Weiguang?
Yeah. So if I understand you correctly, that you are basically trying to say that doing simulation is better than doing this large language models or something like that, right?
In many situations, yeah.
Yes, but taking into account that simulation itself is also dedicated to some particular scientific, let's say scientific questions, right? So it's like large language models. So, to my opinion, is that is back to the people who want to understand something, which one is different, right? You want to understand faster or currently or into a large broad area or things like that. It's all have different aims, let's say. Which two, to me, is just like two, simulation or large-scale language models. Which one works better, and that is people's choice. So regarding to the cost, especially the electricity cost, I actually have a question, is that training the model or using the model, which one costs more electric energy, right?
Training, isn't it?
Training.
But think about that right now, the internet, so many people is using it, even providing this service, and each one just make one query, and it still costs a lot.
Still mount up, yeah.
Yes, and times up, I don't know, right now, like over 1 billion people using it or something, then it's can have a lot of, it can cost a lot of energy as well, right? So,
but to answer your question again, the thing that I was saying is the foundation models is the way they're trying to break up knowledge, say in sciences, so that each sector will have a foundation model that you can go to and get the answers out. So the ensemble of those might be the equivalent of some human in a deeper sense, yes? That's what the agenda is.
The agenda is. And I think there is a recognised thing called Gartner hype cycle, so you get a curve that goes up, and then it drops off into the trough of disillusionment. But that's when the real delivery starts happening. And I think there, it could be that rather than having these big models, maybe people would use smaller models for specific purposes, and that they know work. And then you've got the curated data that you can back it into as well. That sort of feels like where it might end up.
I personally feel that we've got to know what the models are doing and feel they're reliable. So the idea of just keep on expanding, it doesn't fill me with much confidence.
Do we have any questions online also?
No, we do not.
No questions online. Okay, just to make sure. Oh, yeah, Sarah.
Thank you.
So mine might be a little bit unfair because, of course, Kate isn't here. But I was very curious about the last slide that Kate very kindly shared with us during her interesting presentation. That was something, and I'm summarising now, it was something like, quantum computing does chemistry better. Or something, and I was very curious about the specifics of what the quantum computing has actually achieved in the area of computational chemistry. So what sort of molecules have been solved by quantum computing, and what has actually been computed, and what hardware have these calculations been performed on?
So yeah, that's because quantum chemistry is quantum by nature. Quantum computers can be very well suited for modelling that, because they can explore all the possibilities. And to date, it's only been small-scale problems.
So what specific problems, please, have been looked at with the quantum computer?
I expect they've, well, for a start, I know they've solved the hydrogen atom. Beyond that, no.
I solved a hydrogen.
I can tell you. I can tell you the answer to that. Well, first of all, here's the hype. 2017, Google had the cover page of Nature. Remember what I was talking about earlier? And they were on the front page of Nature for solving a problem that, by some standards, is still to be paralleled, using 12 qubits of Sycamore, 12 out of 52, to solve a string of 12 hydrogen atoms in a row, a problem no one's interested in, but they used a quantum computer to solve it. Yes, but you're interested in electronic structure, and you know what I'm about to say. It was a Hartree-Fock problem that they solved using a quantum computer, which is so trivial that no scientist would waste their time on it. Hartree-Fock is the most basic level. The point about a quantum computer applied to quantum chemistry is to solve electron correlation problems. And if you ever start anywhere, you start from Hartree-Fock, and then you build other things in. So the quick answer to that is, we have, for example, a solution to the nitrogen molecule. Why is that interesting? It's a highly correlated set of three bonds, triple bonded, right? It needs something like 20 qubits to solve that problem if you do it in brute force terms. And no quantum computing device at the moment can play a tune. By that I mean get any sensible results out of it with 20 qubits. There's too much noise and errors. What we have done in a paper that's still waiting to be published is solve that problem using 5 qubits, where we can get a signal from the noise.
What do you mean by solve?
I mean, then we have the
calculated the energy levels.
I'm talking to you about it. It's solving. It's calculating the atomic potential between the two nitrogen atoms as a function of distance. That's the chemical bond.
Can't I do that with a pencil?
Yes, now I'm going to say...
Can we maybe move that discussion to later and then finish up
very quickly, though, you can calculate that problem exactly using full configuration interaction. That scales more than exponentially in the size of the problem, but you can do that on a conventional computer, so we know the answer. What have we done? We've done a calculation that can't match full configuration interaction, but it's actually in the Goldilocks zone she was referring to, because it does do better than coupled cluster, single, doubles, brackets, triples, and you understand my terminology. So it's actually in a little area where it's doing better than the best approximation, but we don't need the best approximation because we can do it exactly. At some point in the future, we'll have more, and we'll be able to do something new.
Probably enough on this panel now. I had a couple of other questions which I just scrapped. I also had planned to ask the panelists whether they want to say anything more, but I think we should give Alison all the time for her keynote now and thank the panelists.
Thank you.